Okay, good. So we had seen in the last lecture what an augmenting path is in the residual graph, and we saw what are the residual capacities, and then we defined this procedure which was called augment, which was basically pushing more flow on the augmenting path, right? Now, one thing we wanted to show was that this f prime that we get after augmenting a path, after the augmentation procedure, is actually a flow, right? So let's prove that first.
Excuse me, sir.
Yeah.
Sir, I had doubt means in the process of augmenting the path when we consider a new flow, means how do we modify the residual graph? Could you please explain it once more?
So residual graph, you again you get the f, the new f prime, whatever the new f, which is f prime, and then you put f prime is equal to f is equal to f prime, and then residual graph's definition exactly remains the same. That you have this for every edge, you have a forward edge if f is less than c, and you have a backward edge if f is greater than 0. So you make the augment the new graph every time you have a new flow according to the new flow.
Sir, in that we only consider the path in which we are considering the new flow, for example.
You
So,
can do that, but I'm just saying that I'm just telling you a bad bound for now because it will not matter. This is not going to be the bottleneck.
okay, sir.
Okay, good. So we need to show that f prime is a flow in G. Okay. So now, how do we show that? So for this, we need to show the two constraints. For flow, for anything being a flow, there were two constraints, right? Which were here conservation constraint and capacity constraint, right? So, I mean, the, okay, all right, right. So let's say first capacity constraint. Okay. So only need to check on edges of P because only for these the F value changes. Okay. So basically what happens is, look at the bottleneck, so, okay, let me write the equation and then. So what is F prime E? F prime E is equal to Fe plus bottleneck of P comma F, right? Is less than or equal to Fe plus what is the bottleneck? Ce minus Fe. Bottleneck is, the minimum value of this. So of course, Ce minus Fe is going to be greater than or equal to this bottleneck. So this is like greater than or equal to this, and this is exactly equal to C, right? So what did we do here? We did that. We wanted to show that this f prime E is at least 0 and at most Ce. So we started with that. Okay, this f prime E is at least Fe because it is Fe plus something, right? Fe plus bottleneck. So it is at least Fe. It is at least 0 because Fe is Fe is non-negative, and then we add something to it, a non-negative quantity. So this is fine. The left hand side. Then we just write by definition of f prime E, it is Fe plus bottleneck of P comma F. And what is this bottleneck? Bottleneck is the minimum value of C minus Fe on this path. So basically what is happening, I mean, so you have a path and you start with C minus Fe, and whatever the minimum value of C minus Fe is over all the edges, you increase the F value by that much. So of course it is not going to cross CE for any edge. right? That is the idea. But this is the formal proof, and I will not spend too much time on it. But if you have any questions about what I have written, please ask quickly. Or in the intuition, if you have any question. The maths, you can work it out. So this is the path from S to T. We look at the minimum value of C minus Fe, and we increase that, only by that much. Okay. So, okay, this is for forward edge. Sorry. So, because for forward edge, we increase it. So, suppose this E was a forward edge, then we increase by this much. C minus Fe, the minimum value of that, right? Okay. Now, if it is a backward edge, then anyway we are going to decrease it, right? So what do? We do F prime E is equal to Fe minus bottleneck of, right? So all we need to show now, so of course this is, so F prime E is definitely going to be less than or equal to CE, because it is less than or equal to Fe, which is less than or equal to CE. So that is fine. We just need to show that this is greater than or equal to 0. Is what we need to show. And that is obvious because how much we decrease it by? What is the bottleneck value? Bottleneck value is the minimum residual capacity, and the minimum residual capacity here for this edge. What is the residual capacity? For this edge, the residual capacity is Fe itself. So this is Fe is greater than or equal to the bottleneck. So, and you are decreasing the bottleneck only. So F prime E is greater than or equal to 0 because of this. So basically, what we are trying to show that this thing is a flow, and like we are not exceeding the capacities anywhere in the new one. Any question about this? Okay. So if not, then all right. Now let's go for the conservation constraints. And again, we need to verify that for all V belonging to V minus S comma T, we have this constraint that F in of V is equal to F out of V, right? This is what the conservation constraint says. And now you will have 4 cases. So suppose so of course only need to verify for V belonging to P in the path. And for those V, now there will be 4 cases. So there will be 2 edges, right? So suppose the path looks like this in the residual graph. So suppose it is U, V, W in residual graph in GF, right? Now there will be 4 cases. Case 1, just like quickly, U belongs to, or let's say UV is a forward edge, and VW is also a forward edge, right? Then in that case, there are these 2 edges in G, which are in the same direction as in GF, for which the F value has changed. And this one goes up, the F value goes up by whatever B. Here also F value goes by B. Nothing else changes for V. So Fn is equal to F out. You can verify that. Then case 2 will be, let's say UV is forward, VW is actually a backward edge for some WV belonging to H set of G. And what does that mean? That means that, okay, in G there is this edge UV, which is in the forward direction, but this W is in the backward direction, that is the edge WV. But then this goes up by B and this goes down by B. So total flow in of V changes by nothing and out of V does not change at all. So again, we can show that this is true. And similarly, we can go for case 3 and case 4 as well. Case 3 will be UV is backward, VW is forward. So again, this is backward and this is forward. So now this one goes down by B, this one goes up by B. No, sorry. Yeah. No, then it shouldn't be. Yeah, both are going out. One goes down and one goes up. So this is fine. Both edges are going out of V. So this will change F out. I mean, this will not change, but the only thing that can affect it is F out of V is equal to F prime out of V. Let's say so on. And in one remains same. Case 4 will be both of them backward. This and like this. So this goes down and this goes down. So this shows that in all 4 cases, we have this condition that holds that in all 4 cases, F in of V is equal to F out of V for every edge in the for every vertex V in the path apart from S and T. So we are good. So the conservation constraint also holds, and hence we know that F is a flow. F prime is a flow. Okay. Any question about that? Okay, so this was just to show that, okay, what does augmentation do? Okay, so we had seen an example of augmentation. Now we have seen that, okay, whatever augmentation produces is a flow, and now we are ready to give the algorithm for max flow. Okay. So initially you will put Fe is equal to 0 for all E belonging to E, right? And while there is an ST path in GF, what do? Let P be a simple ST path. And then we find the new F prime by augmenting this path. Then we put F is equal to F prime. Update GF to be GF prime. And that's it. And while. And return the new F prime. Return F because you have already updated F. Right? So this is the algorithm. And this is the obvious thing after doing the augmentation, because that is what we want to repeat, that, okay, whenever we find a path in the residual graph, then we do this thing, augmentation, right? So this is called the fold Fulkerson algorithm. And it was developed in 1956, I think. Yeah. So it is one of the like oldest sort of polynomial time algorithms which is there. Okay. So is the algorithm clear? Any questions about the algorithm? We'll see, the running time analysis and correctness and so on. So let's first see termination and running time. So we don't even know that why this should, why this should ever stop this algorithm. Maybe you can keep augmenting, and because this while condition, there is an ST path. Maybe there will always be an ST path in GF. Right? So how do we do the analysis? So for the analysis, let's just first define a capital C to be summation of E belongs to delta plus of S CE, right? That let's just take the outgoing edges from S, all the outgoing edges from S, and their capacity is C total. Okay, good. So, so let's first talk about termination. Can someone say why will this algorithm terminate? So we'll use that all the capacities are integers. Okay, quickly. Why should this terminate?
The maximum flow is bounded by C.
Maximum flow is bounded by C. Okay, good. So let's say that for any flow F, value of F is less than or equal to C. That is good. Okay, so we start with this trivial flow, which is 0. Everything is 0. But now we need to show something else, right? What? Which is that each time augment happens, updates. So this you can say a lemma. Updates F. The value of F increases by at least 1. And this is obvious, right? Because if you go to augment, what does it do? It does, it takes the path. So the path is something from S to, T. And for all these edges, sorry. So this edge, the first edge out of S, right? So this one cannot be a backward edge, right? So because if this is a backward edge, then this is already, you can't push back on this. So what does that mean? So an edge is an backward, I mean, there can be a backward edge. But you don't decrease for the path. So if this edge is the backward edge, sorry. Yeah. So the first edge, look at the first edge E, right? So since the path is from S to T in the residual graph GF, then we push like, this edge has to be a forward edge because S does not have any incoming edges in G. So if this was a backward edge, that would mean that S would have some incoming edges in G, which is not possible. This is not possible. So this has to be a forward edge. And for this forward edge, what do? We put f prime of E is equal to f of E plus something, bottleneck. And you can check that bottleneck of, P comma F is going to be an integer if all the capacities and the previous flows are integers. You can show this by induction. Okay, so this, of course, and this quantity is non-zero. So we get that f prime E is greater than f of E. Or f prime E is greater than or equal to f of E plus 1 actually, right? And this is an integer, this is an integer, everything is an integer because you will always be doing operations between the integers. So that is why the value of the flow increases by at least 1, right? So this is the proof of this lemma. And now we are done for the termination. So since the value of flow increases each time it gets augmented by at least 1. So, and initially it's 0. So proof of termination. In each while loop, VF increases by at least 1. So, and VF is less than or equal to C. So total C times the while loop will run. Right? Okay, good. So this is termination, that is done. Now the running time. So running time, we want to say that, okay, each iteration of while loop takes order m time. And here by order m, we want to say that since m is greater than or equal to n over 2, why? Because every vertex has an edge incident on it. So we can say that order m plus n is equal to actually order m. Just so that we don't have to keep writing m plus n because m is greater than or equal to n. Okay. So we'll be writing order m plus n as order m. Okay, good. So we want to say that each iteration of the while loop takes order m time. So total running time will be what will be the total running time? Anyone?
Order MC.
Order MC, right? M times C. Okay, good. So now we just need to show that every iteration of while loop takes order m time. So let's just first look at the augment procedure and how much time this can take. So this is the augment procedure. We first, okay, augment already has found a path. Okay, so we'll look at the finding the path. Now, but for each edge, it does something of the path. And how many edges does the path have? It has at most n minus 1 edges. So the augment take n minus 1 time for generating this new flow, right? So I'm just like, getting this out of the way first. So augment takes order n time, which is fine, which is at most order m anyway. Now, while there is an ST path, so first we need to find an ST path. Find ST path in GF This is order m plus n, order m time, right? Because GF has at most 2m edges. If m is the number of edges in in G, right? So this is order m time using whatever BFS, DFS. Okay, so you can find the ST path in order m time. Then what do? Then you do the augment that we have already argued. And then you want to update GF to be GF prime. And that can, again, for each edge in G, now you can update edge in GF prime. So again, order m time. But as somebody was suggesting, you can do it faster by just updating the edges which are there in the path for those edges. And it can be done in order n time, but order n is order m. So we are not really going to care because m is at least n over 2. Okay? So that's it. So this finishes the running time analysis because this is all that the procedure is doing. It updates, and then the while loop we have already argued that it runs C times. So total time is order MC. Good. So now we still have not proved the correctness though. We have done the proof of termination. We have done the proof of running time, that how much time the algorithm will take. But we have not done the proof of correctness, that this actually returns a maximum flow. Right? Right? So that we have not yet discussed. So for that, we will need, this concept of, let's say, cuts. Okay, so let's define an ST cut. So an ST cut in G is equal to V comma E is a partition. We had like sort of informally defined it. Partition AB of V such that S belongs to A, T belongs to B, right? And capacity of a cut AB is CAB is equal to summation E belongs to delta plus of A CE, right? So you have this cut where you have A and B, and you have some edges going out, and you have some edges coming back. And S is inside here, T is inside here, and this is the capacity. So now we will, analyze the flows in terms of these cuts. So that's why the max flow, min cut, and things like that. Because somehow, as we had seen earlier, that this value of a flow cannot really exceed this capacity, right? So we'll show that like a bit more formally now, right? So what does the lemma say? So the lemma says that, we'll build up to that. Let's just say let F be any ST flow and AB be any ST cut. Then value of the flow is equal to F out of A minus F in of A. Okay. So value of the flow is going to be these guys, here minus these guys here, right? And that is actually not very hard to see, because if you just say this, that so we can say that value of the flow F is equal to, by definition, E belong to delta plus of S F of E, right? And we can minus from it E belongs to delta minus of S F of E, because this we know is 0, right? This is basically F out of S minus F in of S, right? We had defined F out and F in. And we know that for every other V, F out of V is equal to F in of V. V in A, let's say, because T for T this is not true. Or F out of V minus F in of V is equal to 0, right? So good. So that means we can sum these up, because this is 0 and this is exactly F. So we can say that V of F is equal to summation F out of V minus F in of V for V belongs to A, right? And why is this true? Because this value is 0 for everything else apart from S. And for S, this value is exactly the value of the flow. Okay. So is this clear? But now let's say, what is this F out of V minus F in of V? So look at an edge and look at how it will be counted. So there are 4 kinds of edges now. So you have this A and B. Okay, so look at an edge UV, or let's say edge UW, right? And you have this A, you have this B, right? If an edge is inside, so I want to see that how many times the F of E will be coming as positive or negative and so on. So if both U and W are in A, then it will be counted for out for U. So F of E will occur as here positive once and negative once. Okay, so this will cancel out. This will not show up in the summation. What if U belongs to A and W belongs to B? If the edge is like this, right? Then what happens? Then it will occur as positive for the U. So F of E will come as positive for U, positive once, let's say, and that's it. There will be no negative because W is outside. We are not summing over W because W is in B. W is not in A. Similarly, if U does not belong to A and W belongs to A, that means the edge is like this, and then Fe will as negative once. And if both do not belong to A, then we have that Fe does not come because the edge is here somewhere. And we are just summing over the V belonging to A. Does not occur in this side. Right? So what does it mean? That only the edges which are going out and coming in, they only occur in this sum, and exactly once the edges which go out come exactly once, and the edges that come in come exactly once, right? And which is exactly basically this quantity. So this, call it 1. So from 1 we get that F of V of F, sorry, is equal to F in of A minus, sorry, F out of A because the outgoing edges occur as positive. F in. Okay, I'm here skipping one step where I would write it in the summation form, but this is what it is. And this is what we wanted to show, that V of F is equal to F out of A minus F in of A. So it was just some manipulation of inequalities and looking at them closely, that, okay, what are the edges which go out and so on. Okay, good. So similarly, we can show that V of F is equal to F in of B minus F out of B. V of F is equal to, we know that, F out of S. And from this, actually, we can show that V of F is equal to F in of T. Right? Good. Because here, if you put B is equal to just T, then you will get this, because T now does not have any outgoing edges. So this will become 0 for T. And then you will have only this in part there. Good. So now we have shown this. Okay. Now we just need another lemma, and then we are good. So what is the other lemma? That just shows that if F is any ST flow, and ABB, yeah, if there is any question, please ask. Any ST cut, then value of F is less than or equal to capacity of AB, which is what we wanted to show initially, but now we are showing that formally using these things. And how do we show that? Now we know that, now it's very easy. So what is the proof? Now we know what is the value of F. Value of F is equal to F out of A minus F in of A, right? Which is basically less than or equal to F out of A, right? We don't even need to care about F in of A, because if you remember, the capacity of a cut is just the outgoing edges. It does not really care about the incoming edges, right? So we can just say F out of edges, which is basically less than or equal to, or let's write it down as summation E belongs to delta plus of A, F of E is less than or equal to E belongs to delta plus of A, C of E, right? Because F of E is less than or equal to C of E by definition of flow. And now we get this to be equal to exactly the definition of C of A comma B. So now we can show this, but why is this useful now? Why did we do this? Because this seems like a weaker bound, right? Here we are only saying this less than or equal to, while earlier had an equality. But the point is, now this quantity on the right hand side is completely independent of the F. It does not care about F. This is just the capacity of a cut. It doesn't have to do with F. Earlier in the what inequality we had, here, it depended on F itself, right? And we'll see how that will use. So basically now, so this is a final lemma, basically. And it says that so basically now, if we show, okay, let me write that down. If we show a flow F such that there is a cut AB and a cut AB, let's say, such that value of the flow is equal to capacity of the cut, then from this we know that for any ST flow and for any ST cut AB, the value of the flow will be less than or equal to the capacity of the cut. So that means the value of the flow cannot exceed now. Then this F is a maximum value flow. And C is minimum value cut from the previous lemma. So this is all we need to show now. That what the algorithm outputs, whatever flow value the algorithm outputs, for that we need to show a cut of matching value, right? Good. So now the final lemma, what does it show? That if F is an ST flow returned by the algorithm, then there is a ST cut A star B star such that value of F is equal to capacity of A star B star. Okay. So F is maximum flow. And A star B star is minimum valued cut. Right. So all we need to find is that a partition, and partition in what? F is an ST flow returned by the algorithm, right? So when does the algorithm return a flow? Algorithm stops when there is no ST path in the augmenting graph. No ST path in GF, right? So we use this property now that there is no ST path to get the partition. So let A star is equal to set of vertices reachable from S in GF, and let B star is equal to V minus A star, which is set of vertices not reachable by S in GF. And clearly, S belongs to A star and T belongs to B star. Why? Because T is not reachable from S by our assumption. Okay, good. So let's look at this graph now. This is A star. This is B star. Okay, here is our S. And here is our T. Okay, good. So now what do we have? That why is there no path from S to T? So look at an edge which is going out, right? And look at all the edges which are going in. So let's look at GF right now. Okay. Okay. Yeah. So let's look at GF right now. So that means in GF there is no path. In GF there is no path means if this was, so suppose this was a forward edge. So let's write them down in different colors. So these are backward, let's say. And these are forward. Forward. And these are backward. but none of these edges can exist in GF, right? So what does that mean? That means that for each forward edge, so now let's look at just one forward edge. So let's say E is a forward edge. E is a forward edge, or E is an edge, which is there, which this edge E does not exist. But suppose this edge E is there in in G. So what does that mean? That f of E has to be exactly equal to C of E. That is why now this edge does not exist. That is why it does not exist. In GF, right? Now, what about these backward edges? These backward edges also do not exist. So what are these backward edges for? These backward edges are for some edge which is again coming like this actually, E. And for this, there is no backward edge. Okay. So if E is an edge, okay, let's say that E belongs to delta plus A. Reach one more vertex here. Okay. Now suppose E belongs to delta minus A. Okay. And what does it mean if there is no backward edge corresponding to something? Can someone say? When there is no backward edge in the graph GF. What is the F value? When F of E is equal to 0. Because if F of E greater than 0, then there will be a backward edge. Right. So what does it mean? It means that for all the outgoing edges from F, everything is already full to capacity. Like, the F of E value is CE. And for the backward edges, it is exactly 0. The F value is exactly 0. And that gives us our answer. That now the value of the flow is F out of A star minus F in of A star that we have shown is equal to summation E belongs to delta plus of A star F of E minus E belongs to delta minus of A star F of E, and we have now shown that this is 0, F of E is 0 for all E belongs to delta minus A star. Okay, I wrote here A, this is all A star. And so this is 0, and this is exactly now summation E belongs to, so this is less than or equal to summation E belongs to delta plus A star C of E, because F of, actually this is also equal, sorry. Because we have shown that here that F of E is equal to C of E for everybody there. So this is exactly equal to C of A star B star. And this is what we wanted to show in the lemma. That if F is an ST flow written by the algorithm, then there is an ST cut A star B star such that V of F is equal to C of A star B star. So this also shows that this is optimum. As the lemma said, that means that F is the maximum flow and this A star B star is the minimum cut. Okay. So is there any question about it? So that sort of finishes the proof of correctness of Ford-Fulkerson. Okay. So like the flow returned by Ford-Fulkerson is a maximum valued flow. Okay. And also, given a flow, now we can compute a cut also. Given a maximum valued flow, we can compute a minimum valued cut in order m time. How? You first make GF, and in GF you just go and see that which vertices are reachable from S and which vertices are not reachable from S. Right? And for every flow network now you have this property that, okay, you can find some maximum valued flow, and for every maximum valued flow there is a cut that satisfies that, right? So finally the lemma would be, for every flow network, max flow, which is the maximum valued flow, is equal to min, which is what we wanted to show also. I mean, this is a combinatorial thing to say. And yeah. Now there are some issues with this, like, that, okay, we have assumed this to be integers, and, what happens, these things are not integers. So actually when these are not integers, then actually it does not run, you cannot give the bound because we have used the integrality very crucially. But this bound, this lemma, is true for all flow networks, independent of capacities being integers. And that you can see that, we have not used in proving this lemma. It can be shown even if the capacities are not integers, that the max flow is equal to the min cut. So this is a property that holds even if the capacities are not integers. But the algorithm running time will not hold, because it might not even terminate if the capacities are not integers, because the increment that happens might become smaller and smaller and smaller, so you can't really give a bound on when it is going to terminate. So that is one problem with the algorithm. And yeah, so that is it that I want to do for today. And then in the next lectures, we'll see that how we can improve this algorithm and so on. So is there any question about the correctness of the algorithm and, this max flow min cut business? So basically the idea is that, okay, look at the residual graph and look at all the vertices which are reachable from S, and then other vertices. That gives the desired cut, because then you can do the analysis on which edges go forward and backward from this cut. Okay. So any question? Very few of you are left anyway. I think everybody is in festive mood, I guess. So no questions? Okay, all right. So if there are no further questions or no questions at all, then I guess tomorrow is holiday. Even Tuesday is a holiday. So I'll see you guys next week. So exactly 1 week from now. Okay. So happy holidays and enjoy. Take care. Thank you for coming.